Right, yeah, we're staying with sponges, but moving to less cryptic ones. We're going to talk about stromatoporoids. Now, stromatoporoids, of course, are very important reef builders and calcifiers from about the Ordovician to the end Devonian. And apart from their general importance for reef building, they've played quite a role in interpreting the influence of aragonite-calcite seas. That's the inorganic precipitation of aragonite or calcite through the Phanerozoic, and how these aragonite-calcite seas might dictate and influence and drive evolution of biomineralization. The problem that we perhaps have is really understanding what the original composition was, because stromatoporoids preserve very oddly. If you look at them in cross-section, just with a thin section, you often see what you would consider fairly well-preserved material, like here, where you get these horizontal laminations, these vertical pillars, and in between the pore space, as you would expect of some sponge. However, if you look at the same thin section at gross polars, it looks horribly recrystallized, with big chunky crystals cutting across everything you've seen before. So it's really a conundrum of how to explain the preservation and to make heads or tails of the original preservation. Some authors argued this really coarse recrystallization must have originally reflected aragonite. Others say calcite. Some say this group was aragonite, that group was calcite. So it's whatever you adopt, you need to explain how you preserve this. And this, of course, in turn will have implications for how you look at how aragonite-calcite sea conditions would drive skeletal mineralogy. Now, what I did is use electron Beck scatter diffraction analysis. And electron Beck scatter diffraction is essentially an SEM technique that gives you information about the crystallographic orientation and nature. So these are highly polished thin sections, and both of these images here essentially come from one scan. The colored image shows you the orientation of crystals reflecting their crystal axis. The black and white image gives you the signal strength that you get. The brighter, the more signal, the darker, the less signal. And to walk you through a bit, these, I used the mouse so you can see them both screens. These lines demarcate the skeleton, which is in the center, which in the black and white image is a bit more speckled and porous, and cement in the cavities, which is a bit cleaner and smoother. Now, if you look at the color image, you will also see that the cements are a lot cleaner, and in the skeleton, it almost looks like you get watercolors that kind of mix with another. You get these smeared out areas of a similar color, like here, but clearly merging in areas. Another thing you see, that there is a continuation of crystal growth from the skeleton into the cavities. So what we do have here is essentially syntaxial overgrowth of the skeleton into the cavities. And that is quite significant because you cannot really imply that this was originally aragonitic, and you get a calcite cement continuing the crystallographic orientation. All of this is now calcite. So to really get more information and to get some reference material from other areas, so to one point I should have said, I looked at sponges from the Devonian of Belgium and from Gotland, so that's Silurian, about 5 or 6 different types. And we get these patterns in all the specimens that I looked at. But I also looked at a specimen of a ketitid sponge from the Buckhorn Asphalt, and particularly because the Buckhorn Asphalt, for those of you who don't know, is a late Carboniferous deposit that was impregnated by asphalt, or not Seuss sedimentary, but before lithification. So the asphalt preserving all of the mineralogy excellently in there. It's famous for its aragonite preservation. So I thought, let's take a sponge from a deposit that we know preserves aragonite, and let's have a look in EBSD. A bit about the morphology. So ketitid sponges typically have these polygonal tubes. That's a cross-section, that's a longitudinal section, which gives you a bit of an orientation what to look for. Here's an EBSD image as before, but this time I merged the two images in one, so the black and white image is kind of the background of the colored image here. You can see the sponge wall with all the smaller crystals here, and the cleaner, bigger colors on the side, cement. We're not interested in the cement, so I blinded out. You see a prominent gap between the skeleton and the cement in many places, and that's where the organic material, like the asphalt residue, still sticks to. And what you can see here is very similar actually to the stomatoporoids, in that you have prominent areas that have similar orientation but slightly different. Each individual crystal, the crystals are much smaller now, but each individual crystal has a similar orientation, and it almost reminds me of bushes of longitudinal crystals that you cut. And you look down, and for every single crystal you have a different crystallographic orientation because the crystals rotate around. And if you cut them horizontally, you get a slightly different orientation with a trend in one direction. Now, if we compare these two, you see that these domains of similar crystal orientation resemble very closely in size and general appearance to these domains here. So essentially, we can use the ketitid to get a better idea of how these clusters were before, like at an earlier stage of diagenesis. Essentially, a cluster like this here would have been composed of many more small crystals that had individual crystal orientations, and somehow they merged during diagenesis. Beyond this, what about the elemental maps or other compositional information? First of all, both of these groups of sponges are characterized by an enormously high microporosity. So this is one image of a stomatoporoid. I could have chosen at random any image I looked at. They're all, the skeletal walls are extremely porous. Here's the ketitid, also porous, but you also see a speckled, very dirty appearance. And all of these red arrows point to microdolomite inclusions. There's also microdolomite in here, but it's not so well visible in this image. So if I move to an elemental map of a stomatoporoid, the yellow line cuts off the pore space up here. You have the skeleton here. And this is a magnesium map, and it shows you where all the microdolomite is. So it's quite common to find the microdolomite in there. Now moving to a ketitid. Here, backscatter image, you see the polygonal walls, and the magnesium sits, a lot more of it sits actually between the wall and the cement in here, where you also have this a carbon map, the asphalt. So essentially, very early dolomite formation before lithification, this is the first cement really that you form, is magnesium rich, and it's actually dolomite in here. And on top of that, we get some microdolomite in the skeletal walls. So how do we think of the original composition? So the original composition was definitely not aragonite. It was calcite, probably with magnesium in it, which is not unusual. But I hesitate to use the term high magnesium calcite because that's kind of a human-made pigeonhole of 4% weight percent or more magnesium. And I can't tell if there was 10% or 1% in there. Even 1% would form microdolomite to some degree. But certainly not a high control of composition here. I'm pretty sure that the magnesium content probably correlates with seawater composition. So if we look at modern sponges, this is a ketitid, we can see that their skeletal walls are composed of these very fine needles, and the scale here is a lot smaller than the previous images. It's 200 nanometers here, so the width of these is nanometer scale. The length is a few microns. So if we use this sort of information and actually look at the biomineralization model proposed for these modern sponges, we can come up with an idea of how to develop a diagenetic model for this. So here we start off with modern biomineralization in sponges. The white blobs are amorphous grains that are added to these needles. There is a mineralization front that follows the arrows, so it doesn't stay amorphous for long. But sometimes, I think, you might include one of these amorphous grains that doesn't quite nucleate. There are examples that, of this process in echinoderms, for example.
About 2 minutes.
Okay, so we move on getting to merge these in early diagenesis. At this stage, we have the buckhorn asphalt ketitid, and at later diagenesis, we get the more blocky merging of the crystals as we see in the echinoderms. So we can explain this now. This is the big blocky recrystallization, is formed by syntaxial overgrowth very early on. Now, if we now come to aragonite-calcite seas, I use the PaleoReef database, which has about 4,000 reefs in it, and I only pulled out the ones that are dominated by sponges, by calcifying sponges for the Paleozoic, and look at their average composition. It looks like this. The blue line is aragonite sea intensity, and it kind of broadly correlates. Of course, we have stomatoporoids down here, other sponges up here. But if we look at sponge thickness, so thickness of reefs that comes from the same database, it actually looks quite good. So here, this time, I use it as calcite sea intensity because we're looking at the thickness of calcitic organisms, so there should be a positive correlation. And we do get quite a good correlation for the stomatoporoid reef calcite thickness. And that's where I leave it. Thanks.